It's time to start the session, exploring the Android Transform API by Marcel. Please give a warm welcome to Marcel.
Thank you. All right. Hey, everybody. I'm Marcel, and this talk is going to be about the Android Transform API. Thank you all for coming. Now, first disclaimer, this is not a talk about animations. The Transform API has nothing to do with UI. It's about build tools. And let me start off by saying this. The introduction of Android Gradle Plugin 3 embraced Java 8. Now, what do I mean by that? Let's take a look at this small code example. So we have an interface here. It's called inConsumer. It has one method. So it's what we can call a SAM interface, single abstract method interface. Then consider another class which has a static method called process. It has one parameter. It takes that interface, and then it does something with that. It calls the one method that the interface has. And then consider a main method that then uses that static method process, and then as a parameter, it uses something like this to call. And this is kind of an anonymous creation of the inConsumer interface, and then that can be called. And of course, the thing below is called a lambda expression. It's what was introduced in Java 8. And in fact, if you compiled that code in an environment before Android Gradle Plugin 3, the build would fail. And it would say something like, I cannot translate this code. There's an invalid opcode here, and you need min_SDK26 to compile this. And then, without changing anything about the code, just upgrading to Android Gradle Plugin 3, magically, the build is successful. And you could ask yourself, how does that work? Behind the scenes here is a process called desugaring. And if you attended the session about the Android Gradle plugin this morning, desugaring was also part of that in a bit. Just real quickly iterating. Again, desugaring means you rewrite Java 8 bytecode into something that is compatible way back when. So to Java 6 runtimes. And over the years, we've had a couple of implementations of this in Android. We used to use a different tool called retrolambda. We don't need that anymore. And right now, it's actually built into the new Dexer, which is called D8. But it's not about D8 so much, but about this implementation here, the one we had before. It was part of a thing which was also called desugar, and it was a transform. So desugaring before D8 is an example of a transform. Now here is a simplified schematics of what happens from your app's source code to actually getting a finally packaged APK or Android bundle. Again, this is just an overview. If you want to have a more thorough insight into this, tomorrow is going to be a talk by Romy and Amanjit, which talk about the entire process. I'm going to focus on the big block here in the middle. So on the left, you have your source code. You probably have some libraries. They also have source code. All of that gets fed into Java C or Kotlin C, your compiler, and then out of that comes bytecode. And then it gets put into this big box, which is labeled transforms, and then something happens, and then out comes, again, bytecode, but it's probably different bytecode than what was put in from the left. And then that bytecode is then fed to the Dexer, which creates Dex files, and then there's a bit of an abbreviation here, and then some other processes, and you get your APK. Now, we're interested in this middle box here. So let's look inside of it. This is just a list of a few examples of what the Android Gradle plugin, first-party support implements through transforms in some shape or form. So for instance, we have the desugaring that I already talked about. ProGuard hooks into the transform as well in a way. Even though it's an external tool, it still integrates with Android through that. And then there's different other concepts, like Instant Run uses it, Jetifier uses it in some way, Dex archiving uses it, and so on. And that's just the first-party stuff. So you can extend this box. So there's other tools, like the retrolambda I just talked about, and also the database library Realm. They also use some form of transform to, I think, synthesize methods that weren't there before into the bytecode. And we're interested in filling in that blank box on the bottom right. We want to get our own transform kind of next to these guys. So at this point, it's important to make a distinction here. A transform is not an annotation processor. There's a distinct difference. A transform can manipulate different types of content, for example, Java bytecode or resource files. And an annotation processor generates new source code. It's a different unit where these things operate, and they are not the same. A transform is more powerful in that it can handle multiple different kinds of content, and it's even language agnostic. So Java and Kotlin, it's just bytecode to the transform. Now, how do you create a transform? There's a few steps. We're going to go with a local module inside your project, so you can save yourselves the dependency and you don't need a repository where you publish something to. We're going to use the build source module, which is a special kind of project in your project which can host build logic. So you create that, and then in there you add a dependency on this artifact here, the com Android tools build, and then Gradle API is the name of the artifact. And then you have access to the transform API. What you do is you create a class that extends from the base class. It's called transform. Then you implement that. That would be step 4. We are going to use another library that helps us with the bytecode manipulation stuff, and it's called Java Assist. And then your transform just messes with the bytecode and then outputs something new. And then finally, when your transform is done, you go back to your app modules build file, and you can register the transform there. There's an API here at the bottom. It's in the Android block. It's called register transform. You instantiate it, you put it there, and then your transform has a shot in the build process. From start to finish, it gets called in there. The transform API itself comes from the base class. It's an abstract class, so that means you have to implement a few methods. Let's go through these real quick. First, we have getName. It's just a unique identifier for your transform, just a string. Next, we have isIncremental. Just a flag, true or false. Can your transform handle incremental inputs or not? And then these last two, they're a bit more interesting. So we have getInputTypes and then getScopes. GetInputTypes basically says what kind of content is your transform interested in. The primary use cases right now is part of the public API are classes, which is bytecode, or resource files. Our example is going to deal with classes, so that's what we're going to use. And then getScopes, think of that as you kind of explain a bit more what it is about the input types that you want to consume. So getScopes has a few different values. For instance, you can say, I want to deal with classes, but I only want to deal with my own project files, only classes from my project. Or you can say, only classes from test code, only classes from external libraries. So you can kind of narrow down what kind of these input types you actually want to consume. And then lastly, the transform has a method, which is also called transform. It has one parameter, transform invocation. If any of you have ever written an annotation processor, this transform invocation is kind of similar to the processing environment. So it's just an accessor for different kinds of helpers that help you do your thing. The transform invocation gives you access to this, inputs. It's a list of folders where your input type content is. So basically, you get the root directory of your class files, for example. And then it's your job to actually go through those directories and find all the class files, and then you do something with them. You also have reference inputs. The difference between these two is inputs declares all the content that you need to consume. Reference input is all the things that you don't consume, but you still can reference them. For instance, if you need your external library's code to do something in your transform, but you don't want to transform the library code yourself, then that's where you would use the reference inputs for. There's also a thing called secondary inputs. It's just another type of content if you require it. It's mostly used for incremental processing. It's going to be outside of the scope of our use case. Finally, we have context and output provider. Context is not an Android context. It's a transform context. It just has some build info and logging access for us, so it's not that interesting. What is interesting is the output provider. It's basically a factory that you ask for another folder, and that's where your transform needs to output its processed material to. So basically inputs, you get a list of directories, and then output, you ask it for where can I put my stuff. All right, so there's very little documentation about the Transform API, and most use cases that I found online usually deal with adding bytecode for logging, so you know how long a method took. I didn't want to reiterate that, so I wanted to do something more interesting, and that required me to go a bit to the, let's just say, non-official side of things. So I want to have an API backport. Going back to the desugaring, I want to desugar something from Java 9. This is a Java proposal for convenience methods for collections, and that was released in Java 9, which unfortunately we cannot use right now. You can see it says release 9, and it basically demonstrates, or it contains a couple of useful APIs. Just really quickly motivating why this is so cool. Say you want to create a list that has three strings, and it shouldn't be mutable. Java 7, you'd probably use something like this, create a list, add the 3 things, and then call unmodifiable list, and then you cannot modify it anymore. Now this proposal that I just showed makes this thing look like this in Java 9, so it's just one line of code. There's new methods on the list interface, actually. They are called off, and you just say list.off, 3 things, you get back an immutable list. Actually, this looks very, very similar to the factories we would use in Kotlin. It's also called list.off. So that's what I want to use in my Android code, just the list.off. There's actually very, very many overloads of these factory functions. There's some for list and for set and for map, and there's just a very, very high amount of these. For the sake and time constraints that we have, we're going to focus on list.off here. So we want to backport list.off. Now here's the problem though. Android doesn't support Java 9. I just said that, didn't I? So if I write that in my Android Studio, just cannot resolve it. It doesn't compile. Even if the syntax on the bottom is correct, it will not let me compile this. So here's the part where I said non-official before. And there's a reason that this slide has a black background. So I won't go into detail here, but that's what I did to hack Java 9 into my Android.jar, so I could write this in my Android Studio. I don't recommend building your stuff against this. Please don't do it, but I did it because it was fun. If you want to have a look at what this is, check out the slides online if you want to actually do this, but never build against a monkey patch jar is all I'm saying. All right, let's write a transform. Okay, I need to set up real quickly. Just gonna mirror this so you can see my screen. All right, so let's see if this is actually visible. It's big. All right, so it's probably a bit small. I'm gonna jump in. So we have a very small sample application here. It just has one activity. Just my activity. It uses my monkey patch Java 9-ish Android jar, so I'm actually able to write this here, list.off. And I want to, all this screen does is it sets a content view, and then it generates the list using Java 9 API, and then it finds a text view, and then it applies this list to the text view. I want to see this actually show up on screen. So I got my emulator here, my trusty emulator. Let's run this app. Of course, we all know what is going to happen, but I still want to show it to you. Let's open Logcat. And you can see, I don't think the app even bothered opening up because it immediately fails. And it says no such method error. There's no static method called off in the class Java util_list. And that makes sense. It's an emulator running on Pi, but still it doesn't have Java 9. So this doesn't work. So let's close down Logcat. So I want to fix this. I want to see this build and actually not crash at the end of this live coding demonstration. So we go back to the actual project. I apologize that this is very, very small. This here is the build source module in this project. So it is the place where you can host your custom build logic without having to have a dependency. So let's look at my build script. I'm not updated to the latest version, whatever. So the build script here, it depends on 2 things. We have first this Gradle API dependency, which is where the Transform API lives. And then the second one is Java Assist. I mentioned that earlier. So Java Assist is a tool that kind of helps you get down to the bytecode. It's a bytecode rewrite library. If any of you have used Java Poet or Kotlin Poet, it has an expression language that's a bit similar. but its API actually looks more like Java reflection, and also a bit of, it looks also similar to the linting APIs that you can use. So you get down to the bytecode with this, and that's what we're going to use. So let's actually go in here in the build source and find our transform. Of course, because of time constraints, I have fleshed this out a bit, but we're going to actually fill out the important part here. So let's look at this transform implementation. You can see here, this class extends from the transform, and that means we have first the 4 mandatory methods, abstract class. First, we give it a name, just random string. Then we say is incremental or not. Say, whatever, build times, right? Just for the sake of simplicity, let's leave it at that. So we want to backport Java 9, so we are going to operate on classes. Again, I can show you that there are also resources available. The internals actually do use a few more of these content types, but those are the ones that are publicly available to us. So we're going to be going with classes. Then here, get scopes. Remember, this is where we kind of give some details on what kind of classes we want to check. I want to check just project files. I assume that none of my libraries use Java 9, so we only want to have project. And here is the meat. Here's the good stuff. Here's the transform method. So basically, the 3 things that it does on a high level is, first it finds all the class files, puts that into a list. And then it asks the output provider to give us a folder where we can put our stuff. And then lastly, we go through all class files, and then we manipulate them, and then we write them out. Let's go into find classes first. This is where we use the transform invocation. So in here, you can see that this returns a list of CT class, and this is a Java assist type. This is basically the bytecode of a class object. There's also bytecode of a method object, of a field, like just the Java reflection type things you have for Java assist as well. They're prefixed with CT. I don't know what that stands for. So first, we create a list of these class objects, and then we create a class pool. Think of that as a lookup table. That's also a Java Assist API. Think of that as a class pool. You give it a string of a class name, and you get back the bytecode for that class. So we set that up, and then we go through all the inputs. Remember, that was on the slide before. These are all the inputs that the transform gives us. All the classes in the project scope are in here. We go through here. It's a bit nested. There's like directory inputs, and then we go in there, and then all directories that we get, we will get 2, because this is a project that has Java and Kotlin together. We will get 2 directories, 1 for each language, and we walk down this path. We only get the root. We walk down this path, and all the files that we find that actually are class files that end with .class, those are the ones that we want. So we kind of compose the class name for it, and then we ask the class pool to give us the bytecode for them. And we put that all in the list, and then we return the list. That's it. All right, so we have that back in the transform method now. We have that in this class files variable. Then we ask the output provider again for a location of our transform, where it should put the stuff. We just give it the identifier, output types that we want to create, and then some scopes, and then it will generate a path for us. We are going to log this. Here you can see there's a log statement. We're going to log this so we can see what this actually does when Gradle runs. But this here, this for each, where the to-do still lives, this is where the interesting stuff happens. Here is where we're going to manipulate the bytecode. Now, I'm not going to go into detail of all the things that Java Assist can do, because it can do quite a lot of things. We're just going to brush on the surface here. I just want to give you a quick introduction of what the Transform API is capable of doing itself, what it lets you do. So we have the class object. Again, it's a CT class, and that has a couple of methods. The one that's most interesting to us is, I think, right at the top here. Yeah, it's called instrument. This is the hookup point where we say, okay, we want to instrument this class. We want to look inside of the class. So there's 2 variants of this. But we are interested in the one that takes in what's called an expression editor. So this is what we're going to instantiate. And this is a class, it uses the visitor pattern, and you can kind of by whatever methods you override here, you can get a say in what type of expression are you interested in actually manipulating. There's many methods on this expression editor that has different parameters, and the parameters tell you what kind of expression it is that you can probably assume to be manipulated here. If you want to get a say in all the constructor calls, you override this one. If you want to get a say in all the instance of checks, you override this one. We want to backport list.off, and that's a method call. So we are going to use this variant here. And in fact, this is non-nullable, so Kotlin doesn't know better. So all the method calls are going to go into here. So this M now has some info on the method call itself. For all method calls in all of the classes, this is going to run. It allows you some access to what class is this being called on, what's the method name, and then you have another accessor called method, which actually gets you the bytecode of the method if you want to go deeper, and we're going to do both. So we want to backport list.off. So we're going to use these two guys probably. We want to check, is the class name list, and is the method name off? So this we can just put behind a simple conditional. Just ask if is this list, and is this called off? So this condition is now called for all the different kinds of list off calls that we saw before on the autocomplete. We're going to go and implement one of the cases, and then for the others I have prepared something. We're going to backport this variant here, the one that doesn't have any arguments. So if you say list string values equals list off, no parameters, this is kind of the same as if you were to call collections.emptylist, but that is an API that we can use before Java 9. So we're going to look for the list.off without parameters, and we're just going to rewrite the bytecode to say this instead. And that's how we achieve that you can write list off, but it's actually going to be backportable. So what we're going to do here is we check the method and see, does the method call have any parameters or not? Because if not, then it's this guy. If it does, then it's one of the other variants. So we need another conditional here that says if the method, and then we can get more deeply into the method. Method has accessor for the return type of the method. You can replace the entire body of the method. We want to get this. We want to get the parameter types. It's an array of classes, and that is what the method call actually was called with type-wise. So we want to check if the parameter types array is empty. We want to check, does it not have any parameters? We can do that because Kotlin is amazing. Just check is empty. And if we are in here, then we know it's actually list off, no parameters. And this now is the last part. We are going to replace the bytecode. Now Java Assist allows you two ways to do that, a higher level and a lower level approach. Lower level would mean we actually get the byte array and we replace the opcodes. But I'm not intelligent enough to do that. So we're going with the higher level approach of just replacing it through the expression language that Java Assist has. There's one method here which is called replace. You can just, we have found the method call that we want. We can replace the entire thing with a new statement. So we're going to do that. And now here's where the expression language comes into play. There's a couple of things. The Java Assist documentation has these handy for you. Basically, this expression means keep the left side of the assignment the same, and then what's right of the equality sign, that's what we're going to change. We're just going to write what we want this to happen instead. So I think collections is in Java util as well, and we're just going to say empty list, semicolon. So basically this says these calls, just replace the bytecode with that. And that's it. We just backported list off without parameters. Of course, here you would have else, and then you check for how many parameters does it have, and stuff like that. But that is effectively what the transform now does. So going back outside of this instrument block, at the end it says class write file. We write the file out to the output folder. And probably not all of, actually most classes won't have the Java call to backport. Still, write file needs to be called for every input. Every input that the transform invocation gives you, you have to write out, even if no Java 9 APIs are here. Because if you don't write out everything that is given to you, it's lost. The next transform will get your output folder as its input folder. And if there's something missing, it's just gone. So everything needs to be output, even if your transform does not do anything to it. So that's why this is not inside the instrument block or anything. It's just it has to happen all the time. Okay, so now I'm just going to do a bit of magic. So this method actually does all the other cases because I want to show you the result of this, and we don't have time to backport it now here manually. Let's still go through the implementation here. So here's the actual implementation of the full thing for all the list of variants. So it looks very similar, just a few superfluous comments here. Again, we check for Java util_list, we check for off, we get the method, get the param count, and then we have a when statement that checks for all the different types of off methods that there are. So there's one that has a var_args argument. So that's actually mapped to just one parameter, and it has the type object array. So this we get like this. We check param count is 1, and the one parameter we do have has this name. If that is found, we actually use that. We check that with array as list and put add all here, and then we do unmodifiable list. That's just the replacement for this type of call. Then the next case is the empty case that we just backported manually. It's the empty list case. Looks very similar. And then the remaining ones are these here. There's just more factories for low counts of parameters. And then again, the common thing with all of these is we create a string that has the new bytecode. So for this bytecode, we create a new array list. Then we iterate over how many params we got. We add them one by one, and at the end, we call unmodifiable list. And then here at the very end, this replacement, which is the string here out of the when statement, that's going to get fed into the method invocation. And then the bytecode is replaced. And then we log it so that we have some way of knowing that it happened. Okay, that is the transform. I know I'm really kind of rushing through this because I want to show off how cool it is, but it's also a bit time-consuming and stuff, so I want to show you this with a brief example, and then I'm going to give you the example code, and you can just dive in yourself. Okay, so transform is complete. It'll work, hopefully. Last step is we register it. So we go back out of build source and then into the app module. Let's look at this build here. So don't be confused by this Android 1000. This is my hacked version. I just wanted to make it really awesome, so I chose 1000. The interesting part that I conveniently commented out is here at the end. So we have the Android block. Let me make this a bit bigger. And at the end, it says register transform. This is a method on the Android block, and that's where you put in your transform. You can also provide this as a Gradle plugin, of course, and then your Gradle plugin could do this, but you can also do it directly. So we add our Hoget transform here, we instantiate it, we register it, and it will be part of the build now. So let us actually run this. So we assemble our app. Again, I added the info log level so we can actually find what our transform does. And you can see I logged out the input and output directory. You can just have a look at this. So input is called twice. We have 2 directory inputs. And then the first one, it says build intermediates Java C. So this is the Java classes. This is this one here. And then below, we have the Kotlin classes. So it gets called for both. You get 2 inputs. The line below, this is the output folder that is given to us by the output provider. And then below, 2 more statements. It found 2 invocations of this. There's actually a Kotlin file. That's probably just because I didn't make a clean build. It also works for Kotlin. That's what I wanted to show. And it says here at my activity in line 16, it found a list.off. Let's just verify that this is actually where that is. And we can see, yeah, this is actually line 16 here. So this is something that it backported. All right, really quickly, I actually want to run this. Okay, so let us experience the awesomeness of this design. But we can see it doesn't crash, and it actually outputs the list content itself. And, well, why is that? We know. Let's still compare the bytecode of what is given to us and what we output. So this is the bytecode that is fed into our transform. It says list.off, no changes, of course, why wouldn't it? And really quickly here, transforms, you can see we have our own folder, and then in here, all the way down is another myActivity class. This is what we output. So let's just real quickly compare these. And you can see, of course, this is not optimized. I'm not sure how much R8 would do to this, but it generates a lot of unnecessary variables. I have no idea why. But you can see that this code here is pretty much what we output as opposed to this. Everything else is the same, but this part is generated by Java Assist. Okay, and yeah, it ran, all good. Let us go back here. I just want to share this link with you because I have 3 seconds left. These are a few resources that I also found interesting when writing a transform. Thank you so much for attending my talk.